So, today we are going to be talking about A Path Towards Autonomous Machine Intelligence by Yann Lecunn. This paper wants to ask, how could machines learn as efficiently as humans and animals? The way we're going to be doing that is through something called a world model. The way this paper is built is, well, let me talk about that a little bit first. So the way this paper is built. So this is not a technical nor scholarly paper like you're probably used to. This is where Yann tries to use as little jargon as possible. And what he tries to do is he tries to make it as approachable as possible to everybody from a lot of different backgrounds. So you don't need to be some kind of like math wizard. You don't need to be super versed in machine learning to come in and understand this paper. It is extremely beginner friendly in that regard. And also, a lot of the motivations for this paper actually come from some of the things he says, like neuroscience or cognitive science and philosophy, and a bunch of other things. It is a really well-written paper, and I have thoroughly enjoyed it. I really recommend reading this paper more than most other papers that I've ever read. So, now that that's out of the way, let's move on. Let's talk about what this paper is. This paper is about learning how machines learn as efficiently as humans and animals using the world model. So we're going to break this into two parts. So both parts are technically going to be the world model. One part is going to be big picture world model. One part is going to be little picture world model. So big picture world model. What we want to do is we want to have something that can mostly observe the world. We're going to take some actions in the world. We are going to take actions in the world, but we're focusing mostly on observation, because observation is just so rich with information, and observation is a lot less risky. Let me give you a quick example to kind of show this off. So let's talk about self-driving cars. So you want to go to the store, right? Imagine that you want to go to the store and you have to use the road. You have to drive your car on the road to get to the store. A machine learning algorithm, what it's going to do is it's not going to know how to drive the car. So the car is going to have a steering wheel and gas pedals and stuff like that. And the agent has to learn to use that. So imagine there's a cliff to your left. Going down the cliff is an option. You could go down the cliff and you could crash your car and things could be really bad. The machine learning algorithm has no reason intrinsically to believe that it's bad until it tries it and realizes that it does not get the reward. It does not go to the store. But a person will know that. A person will know driving off the cliff is probably a bad idea. That is probably not good. And a human, like a person, is going to know to follow the road because that is the best path to actually getting to the store, because you know where the store is. So that is going to be the main idea. The way that machines learn is it has to learn through many different trials, and humans learn very quickly how to drive, specifically, not quite going off of a cliff, just in general, driving. So how do we maximize that efficiency? Well, let's talk about the three main questions. So let's talk about how we do this. And the answer, of course, is going to be the world model. So how can machines learn to represent the world, learn to predict, and learn to act largely by observation? This is going to be the big picture with the world model. This is going to be the first thing that we go into. The second thing is, how can machines reason and plan in ways that are compatible with gradient-based learning? We're going to be introducing these things on real machines, like on computers, and we have to use stochastic gradient descent to actually train these things. How do we do that? And how can we make these machines learn on multiple timescales? Now, this is a funny one. So the first one right here is, okay, so this middle one's the most important one because that's actually how you build the thing. Like, it's going to be a physical object. It is going to be some configuration of electrons. Yeah, it's super important. But so this first one is going to be what we talk about first. How you represent the world largely by observation. You're going to have actions, but you want to look at the world and learn as much as you can from it. That way, as you go into the future, you're not starting from a blank slate. You're starting from what you understand about the world. So this is really going to help because actions in the world are expensive and dangerous. Expensive in the sense that we are trying to maximize efficiency. So if you are spending too much energy to achieve that compared to what you could, or if you are spending too much time to achieve that, that's expensive. And also it's dangerous because you could fall off a cliff. You could always fall off a cliff. You have to try really hard not to fall off a cliff. So there's that. And that's going to be the first thing we talk about. And then the second thing we talk about is how you do this across multiple timescales. This is going to be the idea that you want to forget. This is the nuance. This is the beautiful idea behind the actual thing we're going to introduce. This is going to be JEPA right here. And it says JEPA right down here, so you can trust me. So JEPA is the idea of focusing only on the important things. You find the important things by looking at everything and knowing what to throw away. Learning what you should throw away and what you should not throw away. So we're just going to assume 2, okay? So we are going to take 1, introduce 1, then we're going to take 3, introduce 3, and then we're going to bring the 2 together. That's how we're going to structure this paper. So let's get started with number 1. Right now we are talking about the world model. So we want to introduce an idea called common sense. There we go, common sense. Common sense is the idea that you use the world model to predict what in the future is going to be likely and unlikely, and how you can use that to reason, plan, and predict. There we go. And so you're going to be able to use the world model for a lot of things, like figuring out what the world may or may not do and using what the world may or may not do to achieve some end. That is what common sense is going to be called. Common sense is going to be hierarchical. Let's talk about that. So here is Yann Lecunn's famous baby picture that he got from Emmanuel Dupont. Or I'm not quite sure how to pronounce that, but that is my best guess at how to pronounce that. I would like to deeply apologize to everybody whose names I am butchering today, but it will not end for the rest of my life, so I hope you at least get some joy out of it. This that we're looking at right now is a baby picture. So as you can see, it's age in months, and it goes 0 to 14 months. And let's look. So the vertical axis is just kind of thrown together in such a way that it kind of collects things that make sense to collect things that make sense, to help you understand it just from an organizational standpoint. But I want to focus on objects. That's why I highlighted it. So one of the first things that you learn at around 2 months, between 2 and 6 months, is object permanence. And after you've learned object permanence, so base idea, object permanence, on top of that, hierarchically, you learn solidity and rigidity. And then you learn like categories, and you learn gravity and inertia. So you learn that objects kind of exist in the world. They're kind of objects that, like, it doesn't matter if you cover it. It doesn't matter if you don't see it. It's still like an object. It's still there. And then you learn that different things happen to these objects. You build on top of these core ideas. This is how common sense is going to work. This is how we want to structure the world model. And this is going to be super important moving on. This is going to be a core concept. Always think hierarchy, 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 hierarchy. If I say something and I don't say hierarchy, I want you to pretend that I said hierarchy. So let's scroll down. So I'm going to introduce a lot of things. So this is all just motivation for the world model. Whenever you're looking at this, think world model is green. That's the only important thing. That somewhat rhymed. I didn't mean for it to. The world model is green, and everything around this is to focus on building the world model so that you can look at the external. Let me scroll down. Okay. Let me do a half scroll. So that you can focus on the world model. So you can focus on the world model, and it gets stuff from the real world, and it predicts what the world is going to do. And then it learns from that, because of course this is machine learning. Everything we're looking at here is machine learning. So let's just fly through these. These actually don't matter so much, but I'm going to briefly introduce them because we're not actually going to build any of these things. JEPA is a class of model that we're going to be talking about, and I am just going to fly by the only example that is given in this paper over what the JEPA can actually be. And JEPA itself is a class of models, and it's going to be used to build this world model. And there's not a lot of actual building. This is all very much an opinion piece of what is going to happen in the future. This is a proposition for how we could build things. So a lot of these things aren't going to be well motivated, so I'm just going to fly through them. So we have the configurator. The configurator is the least understood of all the modules. You know how you have to warm up in order to do something? You have to, whenever you're about to start drawing, you have to just start drawing abstract shapes to kind of get your brain going. Whenever you start playing an instrument, you have to kind of start playing your scales and all that, get your brain going. Whenever you start playing video games, you start out in your training range or whatever kind of games you play. Usually there's a warm-up period to any act that you're going to be doing for a while, just to kind of get you in the groove of it, you know? That's what the configurator is going to do. If we consider every one of these modules, or submodules I should say, to be classical machine learning algorithms, then they're going to have some hyperparameters. The configurator is going to configure those hyperparameters to bring out the important things. It's going to see a thing in the world, and it's going to know that this is the important thing that I need, some specific part of the world model, some specific part of perception, and it's going to focus on that thing. It's going to bring that thing up in volume, and it's going to bring everything else down. After that, we've got the perception. Perception is going to be to where you take the world and you cast it into some latent space. Everything that we're doing has to be in some latent space because we can backpropagate across that latent space. The world we can't backpropagate against. The world is non-differentiable. So we have to take the world and we have to put it through this perception block. Just imagine like a CNN or something like that. So that is how we're going to work with the world. There's going to be short-term memory. We're just going to take everything, just take things arbitrarily and throw them in short-term memory so that we can start to train other things like the world model or the configurator or the perception. So we start to train them. That's what the memory is for. So after that, we're going to have the actor. The actor is in 3 parts. It can tell the world model a possible action. It can do a possible action in the world. And it can estimate what the cost is going to be. The cost is going to come in 2 flavors. It is going to be the intrinsic cost as well as the critic, the learned cost. I'm not going to say cost a whole lot because we're going to say discomfort. We're going to be talking about the discomfort of the agent. We want to minimize the discomfort. So the intrinsic cost is going to be just hardwired. It is just going to be a thing that is set. You're born with it, run with it. And then there's going to be the critic. The critic is the learned cost. The intrinsic cost minimizes some cost. It is going to minimize some discomfort, and the critic is going to learn to generally do that over time, over longer periods of time. Both of them are going to work together in tandem. Aside from the world model, that's about everything. The world model is going to, so you see something, right? You see something or you hear something. We're doing this largely through observation. You're going to take in some observation, and the world model knows this is not the complete picture. So what it does is it tries to complete the picture in space or like in hearing, like you hear a thing and you imagine that it comes from a place and your world model fills in a whole bunch of like information about it. And the world model tries to predict what is going to happen in the future. The world model predicts in space and time. That's all the parts. We made it through it. Congratulations. So let's talk about the world model and how we do it. This is primarily how we're going to observe things primarily and learn through those observations. I want you to always think about that. Largely observation. Observation is cheap and we can learn so much from it. So what we're going to do is we're going to have a motivation from Daniel Kahneman's System 1 and System 2. If you're unfamiliar, System 1, this is the very, very, very short representation of his thing. I'm going to say 2 sentences, so believe it or not, we're losing a lot of nuance. Please go read Daniel Kahneman's book, Thinking Fast and Slow, or watch a lot of YouTube videos on it, or podcasts, or whatever you like to do. But I cannot recommend Daniel Kahneman enough. Yann Lecunn cannot recommend Daniel Kahneman enough. He is the first major link in this paper. I feel like it's worth it to describe Daniel Kahneman more than System 1 and System 2. So there you go. System 1, like imagine moving your hand. You really can't put that into words how you do that, right? You just kind of do it. You just kind of move your hand. That's System 1. It is an automated thing. It is just automatic. System 2 is going to be something like learning to drive a car. You can put that into words. You can put into words the actions that you take based off of these System 1 things. Things that you can easily put into language, use the System 2. Things that cannot so easily put into language are System 1. How important the language is controversial, but that is the really, really quick idea. The things that's built from rationality, the thing that's closely linked to a thing called symbolism, and then System 1, which is what System 2 is built up off of. Well, not intrinsically built up off of. System 1 is going to be a connectionist ideology. Now, of course, if you don't know what these words mean, ignore them. It doesn't matter because, these things are based off of System 1 and 2. Let's talk about Mode 1 and 2. So we have Mode 1, which is based off of System 1. Mode 1 is going to be reactive. What do we mean by reactive? We mean that here is the world model. The world model is not doing anything. It is finding out that it did something. This is the basic thing that you can do. So you have some action, right? And then the actor is the action module is going to predict what the cost of something would be. It measures your discomfort, and you just take some action without even asking the cost. You just take some action to minimize that discomfort. And then that affects the world in some way. That affects the world, so you observe the world after it's changed. You observe the state of the world in some variable. That's encoded in your perceptron, your perception module. I'm sorry, perceptron is a different thing. Your perception module takes this, and then it goes back to the actor, and then the actor acts. And that is the loop. It goes actor, world, observation of the world, encoding of that observation, actor. As you can see, it also splits off into the cost. It also splits off into the world model. You see what's going on in general. Now, you're not required to see, but you do see. And then that's primarily how this is going to work. So the world model in green finds out that it did this thing, and you're always measuring your discomfort. So if things go really off the rails, you can focus on it. The world model can focus on it. But you've only got one world model. And the world model is super expensive and super slow compared to mode 1. You're really efficient if you do mode 1 well compared to doing mode 2 well. You want to do mode 1 as much as possible. However, there's a catch. You cannot backpropagate through this. You see, we have the world right here at the bottom left. The world is not differentiable. This loop includes the world. We cannot differentiate through this, so we cannot learn from this. We can only use what we already have learned in mode 1. Then we can talk about mode 2. So in mode 2, so we're just going to start from the action. It's a loop, so we're allowed to start from anywhere. So we're going to take some action. The action is you observe the world. And so you observe the world and you do nothing else. You blink or something. I don't care. This is going to affect the world. And in the world, you're going to observe it again, and it's going to go into your encoder. So you are going to perceive it, and then it's going to be put into the cost, and you're going to measure your discomfort. And then it's going to go into the world model. And then you're going to say, oh, the actor is going to supply something to the world model. So you got some simulation going on. This is for like 5 time steps. 1, 2, 3, 4, 5 time steps. And so you're predicting over 5 time steps. And so you're going to have an action for each of these time steps. And you're going to predict. This is not like a real world. We are predicting this based on the output of the world model. This is all in your head. This is all simulation. We only observe the world once. And then we don't. And then everything is encoded into your latent spaces of your different modules and all that. That way we can backpropagate through this. That way we can actually directly learn from this. So you use that and you predict something, and then you, no, you don't predict something. The prediction is the state of the world. And you use your action and as well as your cost to figure out what is my level of discomfort and what action can I take to minimize that discomfort. And then you move on to the next step. And you predict what the state of the world might be, and then you move on to the next step. And maybe you try it and you run through your 5 steps and you hate it. So you get rid of it. You just do it again. You just say, stop, this is stupid, do it again. Actor module, give me a whole bunch of new actions. You can do this as many times as you like. This is going to be your mode 2. Mode 2 is extremely slow. It is extremely it is much less energy efficient than mode 1. And you're using your only world model. In this paper, we're assuming you have one world model. So anytime you're using it, it better be for a good reason. It better be for something that you want to learn. Now, how do you know what's in mode 1 and mode 2? Well, ideally, everything's in mode 1. It's more efficient. We're trying to be efficient. The whole point of this paper, the very first line, is how do we make machines more efficient? We want them to be efficient like animals and humans. So what we're going to do is we are going to always try to train the actor to learn what the cost would say. That way we don't have to use the world model. Do you see how that is pushing mode 2 options to mode 1? That is learning new skills, as I've just highlighted right there. Look at that, I can highlight things. So this is our introduction to what's called an energy model. Yann Lecunn loves energy models. He also loves self-supervised learning. So the idea of an energy model is extremely simple, and you have come across it many times. Any machine learning algorithm can be posed as an energy model. Imagine the cost, okay? No, not the cost. I'm sorry, that's not a part of it. The loss. In classical machine learning, imagine the loss function. You know how you start at a point in loss. You have some finite loss for your batch, and you use stochastic gradient descent to move down the lost landscape in order to find some local minima? The energy is exactly that, but it's at inference time. The idea is that energy happens at inference time. So the output is you put in two things, and you get some number out. This number is going to be some alignment that you're trying to minimize. You minimize the energy. So what we have is we have the actual output. Oh, I'm sorry, this is all in simulation, so it's not the real output. You have some simulated output of the cost. Some simulated output of the cost based on this action here. And you have what the actor believes the cost is going to be. So you plug those two things and you get some energy, and you use that to train the actor. You train the actor based off of this energy, so it always is trying to be well aligned with the cost. That way, if you come back to something like this in the future, you've already learned it. You've already learned it, and you've already cast it from mode 2 to mode 1. That way, you're more energy efficient, and you free up your world model so you can do other important things. That is super important. Do you see? So we're always trying to force mode 2 things down to mode 1, so we're more energy efficient, and so we free up the world model. This is super important. I'm repeating this because it's super important. If you walk away with anything in this first section, remember that. Also, we're done with the first section, so let's move on. This is how you train the cost function, and it really doesn't matter. We're being so vague with this, and we're really not going to get into anything for this, but I'll cover it briefly. So we have these U's right here. So we have the intrinsic cost. This is the hardwired cost. And there's going to be K of them. There's going to be K hardwired. Maybe it's like a fear of like falling, and it's a fear of like falling in love, and it's a fear of snakes. So like if you see a snake in front of you, your configurator that configures everything and just decides what's more important and less important wants to turn up the snake fear, and that is just going to be an intrinsic fear that is hardwired in, and it's going to turn that up, and it's going to turn everything else down, or some way that makes sense. It's very hand wavy. So that is going to be used, this intrinsic cost is going to be used in order to train the trainable cost, because it's going to take some action. So at first it's only going to use the intrinsic cost, because once nothing is learned, nothing is learned. And it's going to measure the discomfort. And then the trainable cost is going to ask, is there a way that I could have minimized my discomfort further? Of course, as you can see over here, the trainable cost is, it's got some V's that also go through the configurator. So it's going to be trained. The intrinsic cost is going to train the trainable cost. Well, it's going to be some initial conditions, so it's going to be some initial discomfort, and the trainable cost tries to minimize the discomfort after that. So they work together to minimize the discomfort. Here are a bunch of ways that you can do that. Pause it if you like and read that, but it's just reinforcement learning. And then you actually introduce the short-term memory in order to do it. The way that you do that is you have some time step, you have some state based on that time step, and you have the intrinsic energy. The energy is going to be the alignment with it's going to be some energy based on the energy function. Let's just call this the discomfort. Why not? It really doesn't matter at this point. I'll call this the discomfort, and then from there you use that to learn how you can improve the trainable loss, the trainable cost, the trainable discomfort, in order to improve over time. And then we scroll down, we see some question marks, and then we see designing and training the world model. Now we're getting into the interesting part of the paper. Now we're introduced. This is the first step towards JEPA. This is the first step towards the part that tries to forget, that we are going to plug into that first part that primarily learns from observing. So we are introduced to what I believe is the most important sentence in the whole thing. Now, there was the very first sentence that said what we're doing. I'm not calling that the most important sentence, so I hope this bears some weight. At least on my opinion, it bears some weight. Arguably, designing architectures and training paradigms for the world model constitute the main obstacles towards real progress in AI over the next decades. Yann Lecunn, who invented, I think, I might get this wrong, but he invented backpropagation for machine learning algorithms. He invented convolutional neural networks. He invented the idea of energy models, and he is the pioneer of self-supervised learning. Forgive me if I've gotten any of that wrong. He is saying that these world models are going to be incredibly important over the next decades. Now, decades, that could be a long time. I hope I live for decades. I have my fingers crossed for that. That is a long time, or a short time. Between 10 and 90 years. So these world models, I I really think they're going to become really big because I think Yann Lecunn, his opinions are extremely nuanced, and he is telling us a lot right here. And he believes they're going to be important, and he isn't a big name by accident. And also, he is very popular. That's just a fact. So a lot of people are going to start attempting to implement these world models just because he's doing it, and he has just a lot of influence over the world of machine learning as well as deep learning and AI. Uh, so I really think world models will be incredibly important, and I think the sentence is in italics, and that means it's super important. And so there you go. Let's talk about how we're actually going to train this thing. That is going to be in self-supervised learning. So what is self-supervised learning? Self-supervised learning, SSL, is a paradigm in which a learning system is trained to capture the mutual dependencies between its inputs. That is a very general term. Now, why are we using SSL? Why are we doing that? To do that, we have to introduce the cake of Yann Lecunn. As you can see at the top, it is Yann Lecunn right there. And so imagine that you just have some event. Some event happens within an environment by an agent. So that is what's going to be learning. I pose it like this. That way we could just plug in this idea of reinforcement learning. Because technically this could be just any example, any object that you give a machine learning thing with information in it. Oh, I clicked and now you can see the ghost right there potentially. Can you see that? It's gone. Okay, I solved the problem. So let's get into it. The information that a machine learning algorithm can extract from a given piece of data carrying information is not equally dispersed based on the way you train. So if you have pure reinforcement learning, if you have this action, then you receive some reward for having this action that achieves this behavior, or that is this behavior. That is going to give you a few bits for some samples. That is going to give you basically nothing. It's not that it's not important. It's just that it's such a small piece of the cake, a small piece of the pie, that it really doesn't matter that much. And then there's going to be supervised learning. Everything is supervised learning right now. Machine learning is essentially supervised learning right now. And in the words of Yann Lecunn, in the Machine Learning Street Talk podcast, supervised learning sucks. His words, not mine. So you actually just can't get that much out. And also, you're assuming so many things. Whenever you say, here is the data, here is the desired output, it is going to use every single bias in its favor. It is going to use every single pattern in its it can possibly find in order to try this thing. However, that does not imply that every single pattern is good to use. So there's a lot of issues, and also you're just not grabbing that many bits per sample compared to self-supervised learning, which gives you millions of bits per sample. It's so general. It's so general, and you can take so much away from it that it is almost context dependent what you are going to take away from it. Because it is so rich in information, and because we want to primarily learn by observing the world, we are going to use self-supervised learning. Now, we're also going to use energy-based models. That's all the way down here at the bottom right, energy-based models, EBM from SSL. EBM is a subset of SSL here. And I say that because whenever we want to capture the mutual dependencies, if that mutual dependency is represented by a number, which we will call the energy, which you're trying to minimize, then you have an energy model. That's all it takes. That is all it takes. So let's scroll down and look at the next image. This is a generalized representation of energy functions, and it also introduces us to this thing on the right, which I will call an energy landscape. Other people call it that too, so I hope it's a general thing. Remember, the energy is just like the loss. Whenever you have the loss landscape that you're trying to minimize through stochastic gradient descent, you have the exact same thing here. Except this is called the energy landscape. You want the energy landscape to be as rich as possible. You want it to have high highs and very, very low valleys. These black dots here are going to be the energy points, the data points, and they are going to be blue, and they're going to be cool, and they're going to be low parts in the valley. And as you move out and you go towards the tannish colors, then you are moving towards higher and higher energies. So Let's look on the left. This is a very weird representation of our world model. It's a little strange, but it is our world model. Take my word for it. So this is time or space. And what it's doing is it's potentially filling in the information. So what's going to happen is at first you're given an X. An X is just, I don't know, a man throwing a ball or a person delivering pizza. And then Y is, we're going with the pizza thing, it's Y is a person eating pizza or enjoying pizza or grabbing the pizza and saying, thank you for this pizza. I just made this up off the top of my head. I hope it reads. So whenever the two things strongly go together, you learn to minimize the energy for that, for that example. If the two inputs align very strongly, then you have a low energy. And you're going to learn if you see a man throwing a ball and you're going to assign a low energy to it, you might have as output a man catching a ball. That might be a forward guess inside of your world model. Your world model might learn to predict things forward in time or forward in space, because as you know, you can't see everything. And if you just imagine the room around you, that's your world model, filling in the missing information that you're not directly seeing or hearing or experiencing. Now, if we just imagine that this is a video moving and each little tiny slice vertically is going to be a frame, you can learn to predict frames and see how well frames align in between in the blue. And you're given the purple, 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 and then you're given the blue, and you're asked, how well do the blue align? You're going to be able to say, oh, these align well. You're going to train for that. And then eventually you can start guessing what aligns well. And as you can see at the bottom left here, you don't need to be given the entire image. You could be given a crop of the image. If you are familiar with self-supervised learning, then you are very familiar with this idea of getting a crop and then doing some kind of augmentation, some other augmentations on top of that space. Oh, the landscape. I apologize. So that is going to be the primary idea behind the energy model. So if we have that man throwing a ball, and that's the X right here, there's going to be multiple Ys. As we move vertically, there's multiple Ys that align well with it, and we just pick one that is low energy. We pick our favorite one, or we pick them all. We can have an output of a set. There's no reason we can't have an output of a set. So let's talk about the output of the set. So okay, let's go back. So you have the man throwing the ball, and there's multiple possible outputs. However, I want to have another example as well. Imagine that your X is witnessing a car going into a fork on the road. You can either go right or you can go left. So the Y is going to be what happens in the future. So your world model says, okay, I see a car entering this, and what happens in the future? Well, they go right or they go left. So which one do you predict? All of these X's have the same energy. Which one do you pick? Well, they're all good. A car going left or a car going right after a fork on the road. They're both good predictions of the future. Neither of them is bad. So we want to represent both of these. And then in the future, whenever we see Y, Y will eventually happen probably. The car will either go left or right in this example. Then we just want to choose the best one. We want to choose the one that happened to align with that. So we introduce Z. Z is our latent variable. And this is going to make it an LVEBM. I don't have a good way to pronounce that as a word, but LVEBM is the best I can come up with. So this is going to be discrete. Your latent variable is going to be discrete, and it's going to have an entry for car goes left and for car goes right. So you have your X, you see it, and then you push it into the prediction, and then you put Z into it as well. So you go into prediction, I see the car, it could go into the fork on the road. Then Z says, okay, I am the specific Z for the car going left. Now predict it left. And then Z is also the next Z, the next discrete Z, is going to be the car going right. So you have your input, and your output is a set of possibilities. And then Y happens. And what do? You just pick the Z that minimizes the energy. That is all you do. So you pick the minimum Z. So if the car goes left, you pick the Z that aligned with the car going left. That's what you do. Do you see how Z has allowed us to discretize the possible sets of things going into the future that are all equally good? Do you see how that works? To where now you can predict the car going left and the car going right And because these are both good predictions, you just take the better one at the end. They were both good, but this is the one that happened to happen, so we happen to take that. That is our argument for Z. Now let's talk about training them a little bit. I am going to kind of fly through this as you actually look at this. I'm not going to motivate this so well. Please feel free to actually go in and check this out. Oh, I say go in. Just pause it right here and read this. Then pause it right. It's around here somewhere. It's probably just this right here. So I'm going to fly through this. And this is talking about collapse. Now, what we don't want is an energy landscape that is not rich. We want a rich energy landscape. So we can pick the minimum, and we want the minimum number of choices. We don't want, oh, the car goes like to the left and then they stop, and then the car goes left like another foot forward for the next discrete Z and then stops. We don't want too many Z's because that just leads to problems. So the whole idea is we want the energy landscape to be rich and have lots of peaks and valleys. We don't want it to collapse, which is to say that no matter what you put in, you're always going to get flat energy. Flat energy everywhere means collapse. Now let's talk about like classic regression. This right here is whenever you are training your ResNet 50 to decide whether an image is a cat or a dog. This cannot collapse because it's a deterministic function. Whenever you put an X in, that X has a label assigned to it. If you put in an image of a dog, which is, a dog's 0 and cat's 1 because dogs are cuter, so they come first. So you put in your image of a dog, and then that's going to be encoded through this space. And then you're going to have some Y tilde that is the prediction, or Y squiggle if you come from the world of physics, but Y tilde. And you're going to have some Y. The Y is just the true value. It is a picture of a dog or it is a picture of a cat. That is the way we design the data set. So you have a 0 right here if it was an image of a dog, and you have your prediction here, which is a 0. If you put in that image, you're always going to get the same prediction out. It's always going, if we just pretend it's good, you put in an image of a dog, and it always gives you the image classification dog. So whenever you compare it, there's no room for things to mess up. So it is always going to have a rich energy landscape because it either gets it wrong or it gets it right. And it doesn't depend on Y. It is deterministic. So then there's going to be B right here. This is the same thing if you look closely. However, we introduce the Z now. Z comes from the set of all possible Z's. So we're just picking the minimum, the smallest energy based on all of our possible Z's. So we go through it, and then we file through every single discrete option for Z, and we just pick the one that happens to have the minimum energy. But you see now, because we're going through all of our Z's based on our Y, if we put an image into X, we can't say what Y tilde is. Y tilde now depends on Y. If you have an image of a dog or an image of a cat, or you have an image of all possible flowers, or you have an image of all possible cars, and you want to categorize exactly which one it is, if you put in a picture of a flower, do you see what I'm saying? To where Z is the data set that you choose, and the X is just the image of that specific data set. So it's going to be your flowers data set, or it's going to be your cats and dogs, or it's going to be your Titanic. It is going to be one of those. And the Y tilde will align with the Y, the minimum energy, for the correct data set because of Z. It is non-deterministic. You put an image in, and then it is going to have to deal with that and guess which data set it is based on the Y that you're given. So if you're just given an image of noise, do you see? Let's say it's an image of a dog, and then it has to go through and say, oh, look at that. So I'm going to predict this thing, and I'm going to say, if this is a dog, it's this. If this is a picture of a flower, it's this. If this is the Titanic data set, it's this. And this is your set of Y tildes. And then Y happens to be a dog. So you pick the energy that is minimized, and that is the dog data set one. So now, whenever you put something in, you don't know what's going to come out. So it's non-deterministic. Because it's non-deterministic, it can collapse. This is because you can just maximize Z. If you make Z super, super, super big, then you can just have if you just set Z to be infinite, there's going to be infinite lost landscapes, and then you just pick the one that minimizes from the infinite lost landscapes, which is just going to be flat all the time. This is not so well motivated. I could give another answer, but I just don't think it's that important, so I'm not gonna. Next is the autoencoder. This one can collapse because I want you to imagine that we have the identity function right here to the left. So you put in y, nothing happens, y tilde is y, and then whenever y is y, it's going to be 0 energy everywhere because it doesn't matter what y you put in. Then for the x and the y, this assumes that if s sub x and s sub y are two information similar, if they say the same things in their latent spaces, they have the same facts, whenever you put them in, they say the same things because s sub x and s sub y are equal, because they're equal. Not to say they're actually equal. No, to say that they return the same thing. Let's say they just always both return the number 0. Why not? Whenever you put in 0 on the left and 0 on the right, you always get 0 energy. So if s sub x and s sub y are too similar, you're always going to get some minimum energy. If they're exactly the same, you're always going to get the same 0 energy. Where I'm just arbitrarily defining the minimum energy to be 0. Oh, quick aside. So the energy can be turned into a probabilistic model. There's no reason that you can't. But we're not going to, because we really aren't interested in predictions. We're just not interested in actually predicting things, so we're going to keep it as just a number that is the energy. That's just the intrinsic energy. That is just a basic object, an elementary object. The minimum energy can be any number. It could be 1,000,000. It could be -1,000,000. I'm choosing 0 for the sake of simplicity. And that is the quick aside. And that is the possible ways it could collapse. This is going to come up again in just a second. We are going to prevent each of these individually. And we get to another part of training. So this is how we actually train the thing, how we actually take the data sets and contort our space so that we have minimum energy, so that we can actually make better predictions. And we can also have the smallest z, because the smaller the dimensionality, the less you need to do, which is a horrible statement. You know what, let me just walk through this. You have to train it, and this is just a part of training it, so we'll take that. And we'll ignore that last sentence I just said. So the way that self-supervised learning is trained today is through contrastive methods. So how do contrastive methods work? It's actually pretty simple. So you take two things. We're going to take these two things, and what we're going to say is we're going to compare them. And we're going to find out that blue and green are very different. So we're going to separate them because they're different. Or we could take blue and find out that they're the same. And we're going to bring them together because they're the same. Do you see how, with the contrastive method, we warp the space to bring similar things together and different things apart, to warp the space in such a way that it builds this tan part. This tan part is going to be the low energy region. And we want to minimize the low energy region. The more it's minimized, the better predictions that we have, the more we can work with. So the two issues with contrastive methods are, how do you pick your samples? If we pick two things that are already really close together and we find out, oh yeah, those should be together, you're not really doing much. If you pick two things that are already very far apart and you try to put them more apart, you're also really not doing much. So there has to be some smart way of sampling for you to get the most out of every single data point. And of course, whenever you do that, you might make a mistake, and that would be inefficient, and we're trying to be as efficient as possible. The other issue is how many data points you need. You are cursed by dimensionality whenever you start separating the space in this way. Whenever you start doing that, you need to have so many points per unit volume, and the volume just skyrockets as you increase dimensionality. It's cursed by dimensionality. That completely sums it up. For these two reasons, we are going to be abandoning contrastive methods, and we are going to be taking regularized methods. Now, do you see these arrows? What they're doing is they are minimizing the volume of good energy space. That is actually kind of what we were doing right here without explicitly saying it. With these regularized methods, we just take the low energy region and we try to compress it. It is going to be just like whenever we take our L2 norms and stuff like that, because we want the shortest possible thing. We want Occam's razor to apply. So how we're going to actually do that is through our latent variable. But we're not going to introduce that just yet. We're going to scroll down and we're going to find out that we introduce JEPA. JEPA is right here. And this is the whole idea. Do you remember how a long, long time ago, at the beginning of this video, we were talking about how there's the world model, which primarily learns through observation, and then there's JEPA, which primarily learns through the ability to forget. Well, knowing what to forget, throwing away the information that does not matter and keeping the important information. So how is this actually done? This is done by abandoning generative models. We are no longer generating y from x. We are abandoning that idea. This means that we lose a lot. This is a huge sacrifice, but it is worth it because you can learn more efficiently. So what are we actually doing? What we're doing is we're taking x, which is, we'll just say like it's an image of a dog, and y is like a dog barking or something like that. It's just two things that align. And what you do is you take these two things and you put them into a latent space. You put them through your convolutional neural networks or your WaveNet or whatever. You put them through whatever thing you want to cast them into a latent space. And then you put them through and you have some world model right here. And this world model has a certain number of things that possibly could happen. So we're returning a set. S tilde sub y is a set. And this is a latent variable. What you want to do is predict the latent variable of y. You don't want to predict y. You want to predict what y would output. You want to predict what this network would have in its latent space. You are predicting the latent space of y. This is the power. This is where it's super important, because if you're familiar with convolutional neural networks, for example, convolutional neural networks have some kind of basic hierarchy to them, to where the very low levels predict like lines and basic textures. And as you move up, you get more and more exotic things until if you look up Deep Dream, you'll eventually get like snouts of dogs, and you'll get eyes, and you'll get dog shapes. And so you can actually figure out exactly inside of that. Like whenever you imagine a picture of a dog, they're probably like in a yard. They're probably like playing with the ball. The yard does not matter. The ball does not matter. The snout matters. The dog's eyes matter. The dog itself matters. The encoder is throwing away the information that does not matter, and it's focusing on how you actually prepare the information that does matter. The latent space is throwing away information. So whenever we are predicting S sub y, whenever we are predicting the latent space, we are only predicting the important things. Do you see what we've done here? We've found a way to only predict the important things. We've found a way to throw away the information that does not matter. That is the beauty of JEPA. JEPA is a family of architectures, anything that follows this general guideline, this general idea of take two things, cast them both into latent space. We are no longer focusing on the raw objects, because in our case, the raw objects are not even differentiable. These raw objects for us represent the real world in this paper. No, I'm getting ahead of myself whenever we mix the two things together. Let's focus on right now. So whenever we predict the latent spaces, we gain so much. We get so much more powerful because we are only focusing on things that matter. If you have a self-driving car that passes a tree, that tree is so rich with information. Every single leaf. Imagine that you have like you have like 50K resolution images. Not 50,000, like 4K, but like a lot. You can see every single leaf in perfect detail, and you can see its perfect motions, and you can try to predict how those leaves will move. That is extraordinarily information rich, but it doesn't matter. It just doesn't matter. Do you see? That doesn't matter to driving. How leaves move on a tree does not really matter when you're driving. So ideally, the latent space of y is going to know that, and it is going to throw away the information of the tree. It's not even going to try. It's only going to focus on driving itself. Now we talk about how you train it. Do you remember how we said that earlier, like if z is too big, then your latent space is going to collapse? Well, we're going to minimize it here. And also we said that we want to have the regularization method. This R stands for regularization, as far as I can tell. I actually have no idea. It probably says it down here somewhere. I'm sure it says it. So what we're going to do is we're going to try to minimize z, and that is how we're going to compress the space to get away from using contrastive methods. This is the heart and soul of how we actually train the thing to be really good, by regularizing the space to have really, really good predictions. And fewer predictions, of course. This is going to help us avoid collapse. Then we're going to see this branch right here to where x encode x to this red box for I, and the exact same thing for y. This is just saying that we want to maximize the information content between s and x sub x. This helps us make sure that S sub x and S sub y are not equal. They are focusing on x and y and not each other. Because if you do that, it'll collapse, and we don't like collapse. And then, after that, what we're going to do is we are going to minimize the prediction error. We are actually going to go in and talk about whenever S sub y and S sub y tilde and S sub y actually agree via minimum energy. And that's how they're going to work. Oh, by the way, you're probably familiar with energy models through something called CLIP. I'm sure you've heard of CLIP. CLIP is an energy model. So you can really think of that because, you're taking in like the word dog and an image of a dog, and you're encoding both of those, and you're measuring the alignment between the two. Classic energy model. I should have brought that up earlier. Oh, this says everything I just said. And as we scroll down, we're going to see something called VicReg. VicReg is the actual implementation of the thing that we said. And I'm going to ignore it. Yeah, it says everything that I just said, except it's an actual implementation. Now we get into the really cool part. So I said, let me scroll out. So I claimed that whenever you have JEPA, you are throwing away the information that does not matter. What this means is that you can take that, and once you throw away the information that does not matter, you have some set of information, and you can do it again. And whenever you throw away more information, we're not just throwing away information at random, of course. We are training each of these things. So you see this yellow line. Below is one training, and above is a whole other training. So what we do is we throw away the information that does not matter, and we find a way to throw away more information that matters, like only for a certain time scale. So let's give you an example. So we have x sub 0, x sub 1, and x sub 2. It comes up a little glitched here. I'm not too worried about it. So imagine that you're driving a car, and the car in front of you turns on their blinker. Now, let's focus on JEPA 1. They turn on their blinker. This is short term. So this x sub 1 is going to be 5 seconds ahead. X sub 2 is going to be 5 minutes ahead. So much, much different scales. And x sub 0 is where you're at right now. You take your current state and you encode it. You put it through your encoder. You see it. You put it into your world model. Now, you have your z. You have your latent variables. So they turn on their blinker, right? You saw that. So this could mean that they just accidentally turn on their blinker. It could happen. It could mean that they're going to go in the other direction. They accidentally turned it on the wrong way. It could mean that they're going to go into the actual lane that they said they were going to go into. So you're going to have some z, and you're going to have predictions for that. And then you're going to witness it. You're going to witness the actual event, and you're going to predict whether the thing you predicted. You're not going to predict. You're going to have your energy. Your energy is going to be your alignment with what you predicted versus what actually happened. But whenever you did that, whenever you saw that, you threw away a lot of information to get there and make that prediction. But that's not really going to influence anything. The blinker is not going to influence anything in 5 minutes. That is much farther down the road. You're going to throw away more information. And you might say because they use their blinker, they might be a better driver. You're going to take some different information to put into this JEPA 2, which is a completely different model. It's not looking at the same information. It was trained differently, so it knows to look for different things. And you throw away information here, and you have your x2, which throws away a lot of information, then does it again, and then you measure this. So do you see we're working on different time scales now? We have some hierarchical model that works on different time scales by throwing away information. That's the beauty. We can work on this hierarchy because we abandoned generative models and we are focusing on predicting the latent space, where the latent space is good at throwing away information. That is the key. By throwing away information, we are better at learning, and we can do it in a hierarchical manner. I hope I've said that enough times. Well, if saying it enough times actually means anything. So now what we're going to do, we're going to tie it all back together. So of course, everything in the backdrop has been working off of gradient descent. And now what we're going to do is we are going to say, okay, so you have your world that you mostly observe to figure out what's going on. That's how you learn. That's the best way to learn. At least it's the most obvious way to learn. It seems like there's so much information in observing the world and learning from that. And you have your way of throwing away information to focus on what to learn. In this image, we bring the two things together. I'm going to motivate this with a story. It's a very simple story, but look at how we have Actor 1 and Actor 2. This is JEPA. This is hierarchical JEPA. So you have your observation of the world down here at the bottom left. You look in your bread thing, whatever you keep bread in, you realize you don't have bread. This causes you some discomfort, some measurable discomfort, because you want to like make a sandwich or something. I don't know, something that involves bread. So you see the world based on your perception. And then what happens is you encode this because the perception's hierarchical. Like I said, everything is hierarchical. If it's not hierarchical, make it hierarchical in your head. Just it's all hierarchical. So there's going to be some cost, some discomfort because you don't have bread. And you want to minimize this. The actor wants to propose some action minimizing the discomfort for this thing. So you are going to envision in your world model, which is green, you're going to simulate a future in which you minimize this future cost. That is going to be going to the store and getting bread. So we break this down. It's hierarchical. So we have these two predictions of the world. This one right here is going to be I drive to the store, I go to the store and get the bread. And then there's going to be action. I drive to the store. There's action. I go into the store and grab the bread. These things also are going to have some cost associated with them. And from there, it's actually going to break down again how this first one broke down into two different steps based on Actor 2 and Actor 4. And what you're going to be able to say is that you break it down farther. You see how this is like, I don't know, half an hour to go to the store and come back? And then you break it down into just driving, which is 10 minutes, and going and being in the store, which is 10 minutes, and coming home, which is 10 minutes, which would be out to the right. And then you break it down further, and you say, this one is going to be, I walk to my car, I unlock the door, I get in the car, I start the engine, and every single little step, and it breaks it down, and it breaks it down, and it breaks it down. And inside of your world model, you actually go through and you have a complete set of actions that you're going to take to minimize your discomfort in the world. Because of the hierarchical nature, we had an observation, and we were able to take this high-level discomfort, which is about half an hour in time scale, and broke it down into these down to the millisecond timescales of how you actually move your fingers and your hands and all that in order to manipulate the keys and move the car and do all these things. And that is the beauty. We have now introduced a way to completely go through and say, here is how we achieve this very high-level action. Here is how you achieve the self-driving car, or at least one method to it. This is called a method. This is called a path towards autonomous machine intelligence, not the path. I'm sure there's many ways. In fact, the old ways would work. They're just inefficient. We're trying to find a more efficient way to do it. And that is the beauty. That is the paper. This is the heart and soul, bringing together the two ideas of throwing away information and primarily learning by observing the world. These two things, implemented by something called the world model, is how we're going to do this. That is the whole heart and soul. Please take that away. Take that away if nothing else. The three things. Let's scroll back up. We are at page 32. So the three things. Oh, I should have memorized this page number. The three things that we're looking at right here have been solved. These three issues right here. And they give us something incredibly strong. 32. Incredibly strong. And, here is the exact same image. This is actually different from the one above. Down here, we just introduced Z again. Just the latent. So, like, imagine, like, this is actually some set of states that go into and out of your monitor. And those are represented by these discrete variables right here. It can be any depth. Pick your favorite depth. And you go through and you have your regularization to try to minimize the space. And that's how you deal with things you don't know. Maybe you don't know how traffic's going to be. And that's going to introduce some discomfort. And you hate traffic more than you hate, like, not having bread or something. I don't know. Either way, that's actually not so important. The important thing is we made it through and we showed how powerful the world model is. And of course, the world model is empowering us with common sense. Of course, I want to make a very careful distinction. We defined common sense. Not common sense like, we defined it to align with the idea that we already had, and the idea that we had happened to be called common sense. We defined common sense here. Using common sense, we have achieved our goals. And that is a powerful thing. There's a few more parts to this paper. I am just going to fly through them real quick. Please read them with more care than I'm going to go through them right here. So after this, we have the ego. Yes, so there's the ego. They say that the ego, like you, are like more predictable than somebody else probably. So it'd be worth it to have an ego model to help reduce computation and reduce like complexity and all that. That would help with efficiency, keeping track of the world. How do you actually observe it? So essentially, we're going to assign keys and values to everything. Imagine that you have a cup, and the cup was in the kitchen, and you move it to the living room or your favorite room. So we don't want to create a whole new world model based on that. We don't want to create a new representation of the world. We just want to create a new representation of the value of that cup, of where the cup is in space. So we assign keys, and where there would be one specific key for cup, and one of the values of the cup would be, in the kitchen. And you update the value specifically of that key in order to say, now it's in the living room. And that's how you update your world model, because, things in the world change. Then there's going to be data streams. Data streams is just talking about how you actually get your knowledge. We mostly want passive observation because that's so easy. You just fed a stream of data, no thinking. Then there's active foveation. You're fed a stream and you have some attention. You're focusing on a thing. Passive agency. You're doing things, but you're not thinking about it much. Moving up to agency. You can read into that. It's just how you can actually have a model which interacts with the world in more and more passive or more active ways. Then there's going to be designing and training the actor. How we actually do that is really complicated. I completely flew through it. So if you read this, Yann says that it is probably really complicated, and I agree, it is probably really complicated, and I would say we probably don't know yet, but we'll get through a lot of hidden kinks as we go into the future. We'll find a lot of hidden little knots that we have to unweave, that we have to undo. Designing the configurator, he says that this is going to be one of the most important parts and one of the most complicated parts, probably. We have no idea how to do it. He shall leave this open as an open question for future investigation, because actually designing how to set up every single submodule to work the best for that specific situation is very important. It is fundamental to the paper. The configurator was in the backdrop of everything we've talked about today, and we have no idea how to do it. So I'm sure if you do that, you will be able to receive your Turing Award in the mail. Then there's going to be related work. Here are the things that were introduced in the paper. Absolutely beautiful how he goes through everything that was introduced and goes through its motivation. And here is like the main ideas, the main references that he's taking these things from and adapting them for his specific purpose of creating these world models. And just saying like all these ideas, there are so many people in machine learning. There are so many people in psychology. There are so many people, and there is so much to read, and there is so much to do. Having something like this is such a goldmine. Knowing where to look is often such an important thing and such a difficult thing. And for this, I love this entire section. It is such a goldmine. Moving on, energy-based models and JEPAs, joint embedding architectures, or joint embedding models if you like gems more. I kind of like saying gems. It's just, it's a word. So using those is super important, and non-contrastive methods as well as contrastive methods have been popular, but regularization is where Yann is putting his money, so I'm with it, yeah. Human and animal cognition. Is this what we can do to achieve human and animal cognition? Of course, just like the neuron that we use inside of machine learning, it is roughly based off of it, is a simplification of what we are doing, but no, it's not. We're not building animals. We're not building humans. Biology is very complicated and really hard focused on energy minimization. We have different goals. We just have to accept that machine learning has different goals from biology. So this is going to be a separate thing. Could we eventually use this as a model of animal intelligence? God, I hope so. Could this be a path towards machine common sense? Also, potentially. Uh, whenever I say potentially, I want you to actually go through and like start reading these things, okay? And you're gonna find out that he says a lot of words because he's really smart, and the whole paper is really lengthy. It uses a lot of words to really, really, really nail home the point. But essentially, he's saying maybe, which just means that there's so much more work to be done. We really have our work cut out for us, and Yann is not shying away from that fact. And I really adore that. I really enjoy that. Is it all about scaling? Is scaling enough? Essentially, he is punching large language model people and telling them they're wrong. And well, I don't know if he's saying that. That's definitely projection. I don't like large language models. I don't like the idea of them, of just like throwing more and more money at a problem and seeing if that eventually solves it. That's a bad way to solve it. LLMs, they have their merits, but my God, I hope they go away soon enough. They're not going to go away. I hope we recognize that they are not the proper way forward. We have to think of a smarter way. They will always have their place. There will always be the place for a hammer in our tool shed. There will always be a place for LLMs. A reward is not enough. We're saying that reinforcement learning, as I've been vastly oversimplifying it, is probably not enough for what we're doing inside of the actor. We have to think of a better way to do it. Do we need symbols for reasoning? He is essentially asking this question. We are not sure. Whenever we were talking about symbolism, we mainly introduce a vaguely aligned idea of Daniel Kahneman's work between System 1 and System 2. If you are not familiar with those, I really, really recommend you look those up. And then there's the acknowledgements, and we made it through the paper. Congratulations, we made it through. This was just a brief overview to let you know what's in this paper. I really hope that you enjoyed it, and I really hope that you read this paper because it was a wonderful paper, and I would say it is one of the best that I've ever read. I love the prose. I love the big ideas behind it. I love the simplifications. I love the representations. I like these pictures, these diagrams. I really love the way that these are laid out. They're a little confusing at first, but once you get used to them, like I want to use these everywhere. I want to see these everywhere. And that was the paper. I hope you enjoyed it, and I hope you have a good day.